controller designed for temperature control of heat exchanger system, code, design, and simulation studies. Hi everyone! Today I'm going to explain the development and implementation process through simulations supported in the MATLAB interface and Simulink with respect to the controllers implemented to carry out the control of a heat exchanger plant. Let's begin. The first step was the search for an investigation that will allow us to find an optimal process plan to carry out this project. So, it was decided to use a heat exchanger that was characterized by the National Institute of Technology in the Department of Electronics and Communication Engineering. Heat exchanger system. General description. Heat exchanger transfers heat between two fluids without mixing them up. The dynamics of heat exchanger depends on many factors like temperature difference, heat transfer area, flow rate of fluids, and flow patterns. Heat exchanger finds wide spread applications in different industries such as petroleum, food, petrochemical, power generation, nuclear, spacecraft, etc. The basic principle of heat exchanger is shown in figure number 2. Mathematical model. To design a controller, a proper mathematical model of the process has to be determined. Most of the industrial systems are nonlinear in nature and can be approximated as first order plus time delay or second order plus time delay models. The general form of a first order plus time delay model can be expressed like the first equation, and the general form of second order plus time delay model can be expressed as this second equation. Here, Kp is the process gain, tau d is the time delay, tau is the time constant of first order plus time delay system, tau 1 and tau 2 are the time constant of second order plus time delay system. The parameters are obtained from open loop step response data or frequency response data. The time delays are measured from the step response data. Finally, here we have all the transfer functions of every part of the process. So, transfer function model of heat exchanger is the equation number 3. Transfer function model of the valve is the equation number 4. Transfer function model of sensor is the equation number 5. Transfer function model of disturbance is the equation number 6. And the process transfer function is represented as the equation number 7, which is in the form of second order plus time delay representation. So, for the present study, we will take the transfer function of the process in the equation number 7. Without that delays, that is the reason why it remains linear when we ignore the factors that accompany the exponential. Okay? The response of the platform to a step input in Simulink is observed. This has been implemented both in terms of transient function and state variables, thus obtaining exactly the same graphic response as a result. So we're going to run it. Now we're going to see what is on the scope, and the graphic response obtained denotes as a result the gain of 5. That the system has a critically damped behavior as a consequence of the two poles that it has located on the same point of the complex imaginary axis. Here we have an in of 1 and the response of the plant V1 and plant V2, both transfer function and a state variable. Here we can see it is the same, so it was the result of our plant. How we have configured the step? Very simple. It has a step time of 50, initial value 0, and a final value of 1. That is the step in that we are introducing to our system. Cascade control. In the case of cascade control, the plant transfer function has been used as a general process. So, there is a first stage of control that is made up of the actuator process, in this case the valve, which makes up the part fastest of the process together with the experimentally obtained model of the flow disturbance. This makes up the first control loop where PID control number 2 is located. Now, for the second control loop, the sensor model was used in the feedback, with which is possible to control the part of the process that has to do with the slightly slower control action. It should be noted that both controllers were calculated using the auto-tune function of MATLAB, so we're going to run it and to see what is on the scope. The response to a step input for cascade control and a disturbance of 20% is shown in this figure. We have the response in color red, the disturbance in purple, the step in that we have introduced to our system in color green, and the inner loop that is the first loop of our control that I have already explained in color blue. So it is the cascade control for a heat exchanger plant, and it was the result, the general schema, and it has been the cascade control. Feedforward control. In the case of feedforward control, the plant transfer function has been used as a general process. So there is a first stage of control that is made up feedforward control along with the disturbance model. That is the disturbance signal, the perturbance model, the feedforward control, and the general process model. Here we have a saturation block, and based on the above, a pole cancellation PI control was designed that was 3 times faster than the plant to achieve that desired control objective. So, we're going to see what is on the scopes and the response to a set input for feedforward control and a disturbance of 20% that is in purple color. That is that we have here in the figure. We have the step in of 1 and the response for the feedforward control with a disturbance of 20%. So it has been the feedforward control. Anti-windup control technique. For a control system with a wide range of operating conditions, it can happen that the control variable reaches the predetermined limits of the actuator. When this happens, the feedback loop remains at its limit regardless of process output, whether you use a controller with integral action. The error will continue to be integrated further increasing its value. This means that the integral term can become very large and the effect called windup. To prevent this phenomenon from happening, there are two ways. First, introduce limiters in the variations of the reference such that the output of the controller never reaches actuator limits. This often produces limits on controlled operation and does not prevent windup caused by disturbances. Second, another way is the recalculation of the integral when the output is saturated, that is the diagram. The integral is recalculated such that its new value provides an output at the saturation limit. This last case is going to be our objective. And now we're illustrating the Simulink diagram implemented for the case of anti-windup. Here we have a PID control. A PID control in another version, it is just a normal PID, and a PID control with anti-windup and saturation. It is pretty important for our controller. So we're going to run it and to see the graphical response. We are basically making a comparison between these three kinds of PID controls. So, PID, color red. PID control, second version, color blue. And that is our interest, the PID control anti-windup with saturation in color purple. We can see all the cases we get 1 as a result, and it means that the controller has a very good response. Here we can see a graphical for the saturation. For the integral, sorry, it was for the integral. This graphic is for the integral, and the saturation graphic is here. We can see? Yeah, perfect. Most of the industrial processes present delays in their dynamics. A typical example in the industry is a heat exchanger. Delay is a phenomenon that occurs due to a temporal displacement that can appear between two or more control variables, and this can be generated, for example, by the time necessary to transport mass, energy, or information. The following figure shows the control both in the continuous and discrete domain of some controllers that allow the tracking of the reference by means of the implementation of observers. Additionally, a response time has been implemented for the plant, taking into account that in real life all plants have a response time before they are turned on and put it to operation. This generates some lags in the graphical response that are effectively solved with a Smith predictor. Predictor in Simulink. For this part, we have also developed classic observers in order to make comparisons between these different types of controllers. Here we have the first comparison among Smith predictor, tracking reference controller, and a discrete observer controller. Here we can see the graphical response of the comparison made together with the Smith predictor as follows. We have tracking reference controller in blue, discrete observer controller in red, and also a Smith predictor with a delay of 50 seconds. Now we have decided to make a comparison between the classic continuous observer and a discrete reference follower. The scheme implemented in Simulink is this. And the graphic response of the previous diagram implemented in Simulink is illustrated below. continuous classic observer and tracking reference controller step input response in Simulink. Now, the last comparison will be between the discrete time, continuous time Smith predictor, a continuous state observer, and a classical discrete state observer. The graphic response of the previous diagram implemented in Simulink is illustrated here. So, we have the continuous Smith predictor in red and the discrete Smith predictor in yellow. We have also the tracking reference with the observer controller green and the discrete classic observer controller purple. And this has been all for the Smith predictor controller in Simulink. Slider nodes control. The first step to make a controller for slider nodes is to take the transfer function of the process and take it to its state variables. So we have get the following. We have here equation 8, equation 9, and equation 10 with its state variables x1 and x2. The above is the matrix representation of the heat exchanger system. We proceed to find the relative degree, which indicates the number of times I must derive the output until the input appears. Alpha relative is equal to 2, so alpha 2 is equal to 1. According to the relative degree obtained, the controller to be implemented will be a PID controller. We know that alpha 2 is equal to 1, so we can replace that value in the last equation, number 12. So the result is this in the equation 13. For the error equations, we have this equation number 14. Now we're going to derive the 14 equation to get the 15 and the 16. So the general equation is described as follows. We have this, the 17 is gonna be our general equation. We clear it from the equation above. This represents the control action. And now we're going to see the diagram of control action in Simulink for the control of the plant. Additionally, the process states have been taken through a state observer, so that only the input is manipulated and the outlet of the heat exchanger. This is the diagram we have implemented. Here we have the PID, we have an observer, the values obtained, and here is the U, the control action that is going to ingress to our plant, and a reference of 1. Finally, the graphic response of the previous diagram implemented in Simulink is this. Here we have in red the response and the step in, that is 1. We can see it is perfect. Now, for the code part, the first thing is to convert our transfer function system to state variables, and for this we make use the following lines of code. We can also diagonalize our system with the use of canon instruction. Then we proceed with the design of the continuous tracking. For this, we place the desired poles together with the desired poles increased. We proceed to place the increased matrices and find the values of KT, KP, and KI. For the implementation of the state observer, it is required that it be much faster than the plan and thus have a correct estimate. For this reason, the poles are much farther than the desired ones are used. For the classic observer, we perform the calculations using the transfer function, and finally we proceed to discretize all the controls performed using an adequate sampling time. In the final part, we find the 50-second delay time that the heat exchanger plant has for the Smith predictor, together with the values of alpha 0, alpha 1, and eta that have been implemented for the sliding noise control on the PID stage. Finally, we have the code made for the feedforward control. For this, the outlet temperature model has been taken, and the inlet temperature model of the heat exchanger. Then we generate a constant anticipatory control taking these values from the previous models. And finally, for the anticipatory control of the input and output models are divided as follows. Now, for feedback control, we place u equal to the top of the plan and we do it 3 times faster in open loop. Ti is equal to 50 and Tr is equal to 50 divided by 3. Finally, we find the values of the constant Kc and develop the structure corresponding to the PI control. Here we can see it is the PI control that we have developed for the feedforward controller. Okay, it has been all for today. I hope you enjoyed it. Thanks for your attention.